Okay, part 2. Given the sequence, now we're not told if this is arithmetic or geometric, and that's always helpful to know. We need to know what type of sequence we're dealing with. So we got to figure out, is there a common difference between terms? Are they adding the same number or subtracting the same number every time, or are they multiplying by the same number every time? In this case, we're adding 6 to every term. That's an indication of an arithmetic sequence. Okay, and the reason that's important is that's how we are going to describe the nth term. If it's arithmetic, the nth term is going to be described using a linear function, or patterned after a linear function. A linear function is patterned y equals mx plus b. Now in sequences, it's going to be similar. Y is a of n, that's our nth term. M, the slope, can be written using the common difference. The common difference is 6. X in sequence terms represents the value of n, or the term of the sequence. Now b is, in function notation, b is the y-intercept. It's the value of the function when x is equal to 0. What we can do is consider this sequence. This is where n equals 1. The first term is when n equals 1. The second term is when n equals 2. You can only use positive integer values for n to generate terms of the sequence, but if we were to continue the sequence to the left with the same pattern, the term when n equals 0 would be -3, because if you added 6 to -3, you'd get 3, and then 9. So the term when n equals 0, even though it doesn't exist as part of the sequence, would be -3. That would be synonymous to our y-intercept. So the nth term is the explicit function 6n, a sub n equals 6n minus 3. And it's helpful for part B, because now we can find the 29th term without having to write all the terms of the sequence out to the 29th term. A sub 29 is 6 times 29 minus 3. 6 times 29 is 174 minus 3. That's 171. Okay. The recursive formula, or recursion formula here, recursive formulas will always give you a first term and then a way to find the next term based on the term in front of it. That's what this means. A sub n plus 1 means the next term. A sub n means the current term plus 6. So if we know the first term is 5, okay, the term after that, or the next term, if we follow this formula, the next term is equal to the current term plus 6. Well, the current term is 5. If you add 6, you get 11. Now the next term, again referring back to this recursive formula here, the next term is going to be the current term, which is now 11. We add 6. And then we just keep referring back to this recursive pattern here. The next term is going to be the current term plus 6. That's going to be 23. Those are the first 4 terms of the sequence. Okay, evaluate. This is a partial sum because we're only adding terms when n equals 1 to when n equals 15. So we're adding 15 different terms. This is the partial sum of an arithmetic sequence. If we notice the explicit formula here, 4n minus 4, that's a linear function. So this is an arithmetic sequence. The partial sum of an arithmetic sequence, there were 2 versions that were shown. One version is the number of terms divided in half. You multiply that by the sum of the first term and the last term. The other form is the number of terms you're adding up, and then it's the sum of the first and last terms divided in half. You can use either one you want for any situation, but since we're adding an odd number of terms, we're adding 15 terms, you can choose to use this one. If we use the top one, we'd have to take 15 and divide it in half, which would result in a decimal. So if we're using this form, we need to know the number of terms, which is 15. And we need to know the first term and the last term. Those are going to be found using the explicit formula when n equals 1 and when n equals 15. If n equals 1, the first term of the sequence, if you plug in a 1, 4 times 1 is 4, 4 minus 4. So a sub 1 is then going to equal 0. For n equals 15, a sub 15, if you plug in a 15 for n, 4 times 15, 60. 60 minus 4 is 56. So this is the first term. This is the last term. We now have the information we need to use the formula. So the sum of the first 15 terms is going to equal 15, because that's how many terms we're adding, and then 0 plus 56 all over 2. 0 plus 56 is 56. 56 divided in half is 28. So the sum of the first 15 terms is equal to 15 times 28. And that sum, 15 times 28, that's something that you do on paper. 15 times 28 is going to be 420. Okay. Find the 12th term of an n. Now it's important, they told us this is arithmetic. The 6th term. So if we're using a table here, an n and an a sub n, if the 6th term is 17 and the 4th term is 11, what's the 12th term? Now, because this is arithmetic, we know the sequence can be described using an explicit formula that resembles a linear function. So what we can do is find the common difference. The common difference is synonymous to the slope of a linear function. That's the difference of y divided by the difference of x. The difference of y here is 6. The difference in x is 2. 6 divided by 2 means the common difference is 3. So this is going to be 3n. And we don't know what that starting value is here. Remember, this doesn't represent the first term of the sequence. This would be the term in front of the first term, or when n equals 0, synonymous to the y-intercept. But we can use one of these values when n equals 4 and a sub n equals 11. That can help us find that value there. If a sub n equals 11 and n is equal to 4, 3 times 4 is equal to 12. If we subtract 12 on both sides, that tells us we're going to get a negative 1 there. So we know that our function or our sequence can be modeled using the function 3n minus 1. Now if we want to find the 12th term, a sub 12 is equal to 3 times 12, which is 36, minus 1. 12th term is 35. Okay, express the following partial sum using sigma notation. Sigma notation involves the letter sigma. We're adding 1, 2, 3, 4, 5, 6, 7 terms, so we're going to start when n equals 1 and end when n equals 7. What we're missing is the explicit formula here that describes this sequence. So that depends on if this is a geometric or an arithmetic. We've got to decide, is there a common difference or a common ratio, and it appears that we're adding 3 every time, which makes this arithmetic. So a sub n is going to equal 3n, and again 3 because that's the common difference between terms. And if we wanted to know what term would come in front of 2, it's negative 1 because we're adding 3 going in this direction. But if we want to make the sequence in that direction, we'd have to subtract 3. So the explicit formula for this function is 3n minus 1. Okay. Find the 9th term of the geometric sequence. Now, geometric sequence means you're multiplying by a number every time. We're multiplying this by 1/3. 27 times a third is 9, times another third is 3, times another third is 1. So if the pattern continued, the next term would be 1/3, then 1/9, and 1/27. Next one would be 1 over 81. 1, 2, 3, 4, 5, 6, 7, 8. We only need one more. If we multiply this by another third, we're going to get 1 over 243. So, I mean, there's one way you could find the 9th term of the geometric sequence, but it's only because they're asking for a relatively smaller number. If they were asking for the 12th or the 15th or the 19th term of the geometric sequence, these numbers are going to get very big very fast. So another way you could do this is to find the explicit formula. Since this is geometric, it's going to be modeled using exponential functions, b times r to the n. N represents what term of the sequence you're searching for. R is the common ratio, which in this case is 1/3. b, like we were doing with these this arithmetic sequences, b would represent the number in front of the first term, which in this case would be 81. So our function, or our geometric sequence, can be modeled using a sub n is equal to 81 times 1/3 to the power of n, and then if you want the ninth term, 81. And since calculators aren't allowed, you're actually okay to leave it like this, in that form. And this form is helpful if they're wanting a much larger term of the sequence, like the 15th or the 20th or the 80th term. You'd leave it in exponential form. Okay, the sum of the finite geometric series. I'm using words here that you might not be familiar with. Finite means ending or partial sum. Infinite would be the infinite sum. So the terminology I think the book used was partial. Find the partial sum of the geometric sequence. So the hint here is to use this formula. We know the first term, a sub 1, is equal to 1. Now r here, this r represents the common ratio. Common ratio, it's doubling every time, so the common ratio is 2. N is the number of terms that are being added. And this dot 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 means there's terms in here that are not shown that are being added, so the next term would be 16. Then we have a 32 in there, and then we're up to the 64. So we need to count these terms: 1, 2, 3, 4, 5, 6, 7. We're adding 7 terms, so n is equal to 7. So now the formula is going to be a sub 1, which is 1, times 1 minus 2 to the 7 over 1 minus r, which turns out to be negative 1. 2 to the 7th is 128. So this is 1 minus 128, which is negative 127 over negative 1, which is 127. Okay, the sum of the infinite geometric series, or our book calls them sequence, has a different formula. The sum of an infinite geometric sequence is the first term divided by 1 minus the common ratio, and this function, or this formula, only works if the absolute value of the common ratio is less than 1. Okay. Now, if we look at the explicit formula for the sequence, we notice it's an exponential form. Exponential form describes a geometric sequence, and the base of the exponential represents the common ratio. Because 1/11th is the base, that's the common ratio, that's going to be less than 1. So we're going to be able to use this formula here to find the infinite sum. What we need to know is the first term, though. We know that r is equal to 1/11. To find the first term, we need to evaluate this formula when n equals 1. If n equals 1, 1 to the 11th, 1 over 11 to the first power is just 1/11. When you times that by negative 2, you get that a sub 1 is equal to negative 2/11. So the sum is going to equal negative 2/11 divided by 1 minus 1/11. And that's negative 2/11 divided by 10/11, which is negative 2 divided by 10, which is negative 1/5. Okay, 15 is an interesting question. Find the values of x for which this sequence. First, we need to find a value of x that would make it arithmetic, meaning we have to add a number to get it to x and add the same number to get it to 12. We need to find a number that makes it geometric. Okay. Now, if it's arithmetic, it's going to have a common difference. We're going to add a common difference to get x. We have to add that same common difference to get 12. So if we take 6 and add the common difference d, that's supposed to equal x. But if we take 6 and add the common difference and add the common difference again, that's going to give us the next term, which is 12. 6 plus d is the same as 6 plus 2d is equal to 12. Subtract 6 on both sides, and we get that 2d is equal for the 6. So the common difference is equal to 3, which means the value of x that turns us into an arithmetic sequence is 9. Now to make this geometric, that means we have to multiply a common ratio. If we start with 6 and multiply it with that common ratio, that's going to give us to the next term, which is x. But if we start at 6 and multiply by the common ratio and multiply by the common ratio again, that's supposed to get us to 12. 6 times r is the same as 6r squared. That equals 12. If we divide by 6 on both sides, we get the equation r squared is equal to 2. If we square root both sides, we get that r is equal to the square root of 2. So that's our common ratio. So if we take 6 and multiply by the common ratio, 6 times the square root of 2 would be the next term of the sequence that would turn this into a geometric sequence. And that's, I believe, yep, that's the end.